And Jim reminded me, too, I loved a presentation Jerry Franklin gave once because he got a lot of grief for setting up plots without having a hypothesis. And this was at the Ecological Society of America, and he was starting his talk, and he said, "Everyone tells me I need a hypothesis, so I came up with one. My hypothesis is trees don't die." After collecting 20 years worth of data, I have refuted that hypothesis. And I just thought, good for you, Jerry. I like that. I had to think about what talk to give here. This is supposed to be the somewhat more technical talk. And this paper, the paper that I'm going to be talking about, came out 3 years ago, so it's a little bit old. But I think it's really interesting, and I think it's important. And also what's cool about talking about it is it tells us something about how science gets done and where, now I'm doing the little fake quotation marks, where facts come from. So without further ado, I will just leap into it. And first I'm going to talk about the origins. The origins of this study are connected to the collapse of Mayan civilization and the death of Mark Twain. Yeah, that's pretty impressive. I was waiting for the wow from the audience. Here's Ellsworth Huntington in probably the 19-teens. He was a famous geographer at Yale, and he was a climatic determinist. He thought civilizations rose and fell at the whims of climate. And so he had been in Central America and seen the Mayan ruins and recognized that there had been once a great civilization down there that had collapsed, and he was sure that was due to climatic changes. He didn't know where to find evidence of those climatic changes until he heard about the giant sequoias that had been logged in the Sierra Nevada. So the 19-teens was towards the end of the logging of the giant sequoias, but he figured this is a good place to go get tree rings and try to find evidence of climatic changes. And, you know, you got to appreciate how bold he was in that here's a tropical climate, and to understand the tropical climate, he was going to a snowy temperate climate to get the data. He had good confidence there. Here's the death of Mark Twain. This is the Mark Twain tree. This is just an example of one of the huge sequoias that got logged. And it's the Mark Twain tree's stump. And he went with his crew, his field crew, out to those stumps, and they would get down on their hands and knees on those stumps, and they would count out 10 rings at a time, and then they would measure the width of that group of 10 rings. And then they'd count out 10 more and measure the width of 10 more until they had the whole series going back to the pith of the tree. And he got a publication out of that. They did it for 458 different sequoia stumps. And so back in the 1990s, early 1990s, I needed to estimate the ages of large giant sequoias, and this seemed like a huge resource I couldn't pass up. So if you only had a core that went this far into a giant sequoia tree and could measure the length of the core and the growth rate on the core, could you extrapolate the age of the tree, and what would your confidence be, and could you get an unbiased estimate? So that was why I was using his data, and we got photocopies of all his old data sheets, and we put them all in a computer. And here's an example of a time series from one of those giant sequoias. Here's annual diameter growth rates. That's diameter growth rate in millimeters per year. It's a 10-year average for each point. And here's the diameter of the tree. So this is one individual tree growing through time. And I want to point out something here that's really struck me when I was working with these data in the 1990s. Here's a 3 meter, when it was 3 meters in diameter, it was putting on rings that were about 2 millimeters wide. By the time it was 6 meters in diameter, it was still putting on rings that were about 2 millimeters wide. And these trees don't taper. They're almost like cylinders. So if you think about it, the surface area of a 3 meter diameter cylinder, and you wrap 2 millimeter of width around it and compare the mass of that wood to a 6 meter diameter cylinder, put the same width, that 6 meter diameter tree is putting on a lot more mass per year. It's sort of like if you have an onion and you're peeling the onion. If your outermost layer of the onion is as thick as the innermost layer, you know the outermost layer has more mass. So the largest trees on Earth were putting on more mass each year of their life up to the point this one was cut. That struck me as really interesting, and I did nothing with it at the time except like 1 or 2 sentences in a paper I published. They were sort of throwaway sentences. But I started really looking at the literature and saving related papers and holding them with the idea, the idea that someday I would come back and revisit the question. And finally, in 2010, a good funding source became available. I applied for it. We got the funding. And that big list of 37 co-authors, it's the biggest group of people I've ever worked with. Noel Beckman, who's in the back, who will be faculty here in July, was one of the authors of this paper. It was an amazing group to work with, and we analyzed data from all over the world. I'll get into that. Oh yeah, so here's the demonstration. If you convert that ring width or that diameter growth rate into mass growth rate, you look here, here's the diameter of the tree, and by the time it was at its biggest, it was putting on about 600 kilograms of wood a year. And that's just wood. That didn't count the foliage and things like that. And that's an enormous amount of mass. That's the amount of mass you might find in a 30 or 40 centimeter diameter tree. So the outline here, I'm going to pose the problem, go through the methods we used, talk about results for a little bit, and then a little bit on why we think our results are robust. And then this is the quirk of science part of this whole thing. I call it the spontaneous generation of facts. And so really it's what are the origins of the scientific controversy about tree growth rates that I'll be introducing pretty soon. And then why does all of this matter? So the problem is that there have been two mutually exclusive generalizations out there in the literature. One has said that giant sequoia tree growth rates go up and then decline, mass growth rates through time. The other has said they keep going up forever and ever and ever. And I'll use an example of how does human mass growth rate work. So here's ages of humans, here's their mass in pounds. So for white males, I picked that because I wanted to see, I'm about 25 years old, so I should weigh about 160. I'm a little more than that, but what the heck. But to get mass growth rate, you just take the first derivative of that curve, and to get it into pounds per year, and you see, there is this enormous growth in the first year of life, but what we usually think of is when you're pretty young, you're not growing very fast, you go through your adolescent growth spurt, and then you decline again. The question looks something like this. For trees, is it the same thing? This would be the same thing for trees. We put mass on this axis instead of age, and the mass growth rate, or does it go like this? And real briefly, I'll just say, well, why do we even care? It's because forests are for a bunch of reasons, but forests are such an important part of the global carbon cycle. For terrestrial vegetation, they hold a lot of the mass of terrestrial vegetation, a lot of the carbon, 82% by this estimate. You'll get different estimates. And that's almost equivalent to the amount of carbon in the atmosphere in the form of carbon dioxide. So if you vaporized all of the world's forests, you would almost double atmospheric carbon dioxide, and that's a greenhouse gas, and that's why we're so interested in the carbon cycle of trees. And just in terms of productivity, they're about half of terrestrial vegetation's productivity. So their productivity is really big, their mass is really big, they hold a lot of carbon. Here's the first conflicting generalization, and I won't read all these to you, but there's been a long-held camp of people who say growth rate increases until it reaches a certain age, and then it declines again. And this is, that idea is both implicit and explicit in these recent sort of state-of-the-art edited editions. So conflicting generalization number two, these are both out there in the literature at the same time, and the groups just aren't talking to each other, is that growth rate should increase continuously. Metabolic scaling theory says it should, and I will say that metabolic scaling theory gets a lot of grief, and where I think it works best is at the scale of the individual, like an individual tree. Where it starts to get dicey is if you try to apply it to populations, communities, and whole ecosystems. Then the Select group at Humboldt State University in California, empirically, we're climbing big trees and taking measurements and realizing, wow, for some of the biggest trees on Earth, mass growth rate continues increasing through time. And, I liked this study that looked at basal area increment from cores that reached the pith of trees because they found, wow, they were sort of startled that their calculation showed mass growth rate increasing continuously with time. And since that didn't fit this idea that it would decline, they even suggested that maybe environmental changes were driving that. So it is interesting to ask, why hasn't that been, or why isn't it resolved? Why were there two camps that weren't talking to each other with whole different ideas? And part of the reason, I think, is that it's just not easy to look at the usual measurement we take is diameter growth rate of a tree and decide whether its mass growth rate is increasing, decreasing, or staying the same. So again, tree diameter here, diameter growth rate here, all of these are declining, and usually that's the pattern you see in trees, is as a tree gets bigger, ring width gets smaller. But they're all decreasing at slightly different rates, and if you convert those to mass, because this is a one-dimensional measurement, so you have to use some equations, allometric equations, to convert it into three-dimensional mass growth, you find that the uppermost one is continuously increasing growth, the lowermost one is continuously decreasing growth, and the middle one is constant growth, mass growth rate. So it's not easy to just look at a ring width series and make a decision as to what's going on with the trees. So our methods is all we could deal with is above ground growth. There's some theory and some empirical data that suggests the scaling ought to be the same for below ground growth, but we had no way of testing that. We're stuck with dealing with above ground. We also could only deal with gross growth, not net growth. So we could talk about how much mass you're adding to a tree each year. We couldn't talk about how much mass you're losing to something like heart rot. We just had no way of dealing with that. Here's how we estimated mass growth rates. We had measured trunk diameter at time 1, something a lot of us are familiar with doing. And we would use published allometric equations, species-specific whenever possible, to convert that diameter measurement to an estimate of mass measurement for that tree. And the simplest of all allometric equations is just a power function, where the constant is usually between 2 and 3. 22% of our species, that was the best equation we could get. Others are more complex to try to take some of the, there are some biases to this approach to try to remove those biases. Some mass is a function of diameter and tree height. Others were just there was some subset of functions that were just based on diameter. Then you go back to the same tree at time 2, usually 5 or 10 years later, measure its diameter again, and calculate mass growth rate as the difference in mass between those two time periods, divided by the years that have passed. So we needed repeated diameter measurements. We didn't want to bias it in any way, so we only took it from plots where every single tree in the plot was mapped, tagged, and revisited every year, or every 5 years or 10 years. Ended up with those 38 collaborators from 16 different countries, and ended up getting data from all 6 continents that have forests on them, more than 400 subtropical, subtropical, and temperate tree species. We couldn't find adequate boreal data to throw that in. Maximum trunk diameters went up to 270 centimeters. On average, among species, it was 92 centimeters. So these are fairly big trees at the high end, and ended up with 2/3 individual trees that we analyzed. So we had to make some decisions about how to model mass growth as a function of tree mass. One of the early things this was maybe the key one of all, is we didn't want to have any a priori assumption on what the shape of the relationship should look like. And if you pick certain functions, continuous parametric functions, you run the risk of the most data-rich part of the mass axis will affect the shapes at the tails, and the tails were especially important here. So we ended up doing these line segments, that they had to be conjoined line segments, because that would allow at any point along the x-axis, you could make a sharp bend down or a sharp bend up. That was critical. We just didn't want to bias our results by having a function that wasn't flexible enough. So we used piecewise regression, 1 to 4 conjoined line segments, and they were chosen by AIC values. And we had to log tree mass here because the more and more massive a tree is, the sparser the data gets on a linear scale. So for statistical reasons, we had to log that axis. But the mass growth rate axis, it didn't need logging in the first place, but we definitely did not want to log it because we wanted to retain all of our negative values. And I'll just say that we purposely tried to bias our data against finding continuously increasing growth, because as trees got more and more massive, we allowed larger and larger and larger negative values of growth rate. We did not allow larger and larger values of positive growth rate. So we were sort of loading the dice against ourselves. And I want to put in this sidebar because the logging of the x-axis did confuse some people. It was more like it didn't confuse people. Some people were afraid others would misinterpret it, and they'd say, well, this looks like accelerating growth. And it's not. It's just that axis is logged. And if you have a linear axis, it's decelerating increases in growth rate through time. And that's what's predicted by theory also. So results, from every continent, the majority of tree species had continuously increasing growth, and especially in that really critical last bin, that last line segment, 97% of them had increasing growth rate up to the largest trees. I'm going to go back to this. These data are a snapshot in time. So this means that if you walk into a forest and just look at the trees at this point in time, the biggest ones are the ones growing most quickly. What it doesn't tell you is over the course of a tree's lifetime what is its growth trajectory, because down at this end of the curve, there could be lots of really suppressed trees that end up dying before they even make it out here to the end. And so we wanted to get a better idea, if we had perfect longitudinal data, what would be the growth trajectory of an individual tree. So we went to the literature, and you can find equations for not a whole lot of species. I think it ended up being 34 species that where people have done the calculation to fit a model of tree growth rate in the absence of competition. And so we looked at those data too, and they pretty much were the same. So even when you remove the effects of competition, you get continuously increasing growth rates through time for most species. There are definitely exceptions. It's also cool that in absolute terms, really big trees put on a lot of mass per year, and I've mentioned that already. These data I will talk about in greater detail later, but these are sort of the bookends, some of the most massive trees on Earth with mass growth rates calculated by Sillette's team in a whole different way. They actually climb the trees, and I'll describe how they get those numbers later. So really, a tree 1 meter in diameter, all over the world, the average was that's putting on about 100 kilograms of dry mass a year. And if you go up to the extreme, some are putting on, half a metric ton per year or more. Here's why we think our results are robust. I'll go through those 3 points. Methodological artifact. I will not go down in the weeds with these because, oh my gosh, it gets boring quickly. But we don't think it was methodological artifacts. We did more than a dozen separate things to be sure this wasn't a result of bias. Some of my co-authors were getting angry at me when I kept insisting, no, we need to do another test and another test and another test. But we tested for bias in our allometric equations. Does that make a difference? One subset was biased. We removed the bias from it, still got the same answer. Field methods, analytical methods. We could not find a way in which our results could be a result of bias. And there's a lot of evidence from other approaches and studies, or at least enough. Increasing basal area increment with age from tree rings, it's pretty common to see this in the literature. These data, you always have to interpret with caution because you don't know how much of the trend you're seeing is driven by environmental changes that might have been happening over these really long lifespans. I mean, we know the environment has changed over the last 250 years. Climate has changed, nutrient inputs have changed, all these things have changed. So you have to interpret them with a lot of caution. And there are some from Europe, Fagus sylvatica, Costa Rica. Some of these do curve down at the end. And again, you don't know if that's the tree's natural growth trend or whether that might be an environmental change. And there was one study that seemed to, this wasn't even longitudinal data, that showed a pretty distinct decline when you took a snapshot in time approach. And I don't think this curve fits the data. I don't think they used AIC to fit that model. The gold standard is, these intensive measurements that Salet and his team do. They climb the trees at 5-meter intervals going up the trees. They take cores all around the tree to get the diameter. So they measure the diameter, and then they see how much it's grown in the last few years. They go way out on these limbs. I'll give you some statistics here. Here's one of the sequoias they did in Sequoia National Park. On average, more than 7,000 structural measurements per tree that they climb. Systematic subsampling for wood density and leaf mass throughout the crown and the bowl. Cores from all sides of the trunk at regular height intervals. These people are fanatical, and they're great. I mean, they are incredibly detail-oriented, and their first publication was on the world's tallest angiosperm and world's tallest gymnosperm. So eucalyptus from Tasmania, I believe, is where they got it, and then the coastal redwoods of California. And you've seen this graph already, but that was their results. And these fits are pretty darn good. Later, I'll show you coast redwood again, and the fit won't be as good. Here, they had purposely sought out open-grown trees. And the later one, they started throwing in suppressed trees also, and so the relationship isn't as good then. More recently, they've done giant sequoia, the most massive tree on Earth. It's not the tallest, but it's the most massive. And so there's giant sequoia there. Here's the coast redwood with more data points. A lot of these were from suppressed trees down here. And this is actually almost certainly the second most massive tree on Earth here. They're not allowed to climb the most massive. I actually think if they climb the most massive, it's the General Sherman tree. We have some cores that were taken from it in the 1960s. It's growing really fast. And I think if they could have climbed it, its point would probably be up here somewhere. Finally, lack of opposing evidence. This is why we think our results are probably good. This paper stirred up a hornet's nest, and 8 groups responded to Nature with one of these, I want to comment on these paper type things. A couple of them were just, someone saw an opportunity to make a point that they thought was really interesting. They weren't a critique of us, but others really were trying to say this looks like this is impossible. This has to be an artifact. But they couldn't present any empirical evidence that it was an artifact or that tree growth declined with size. So all evidence considered, returning to that graph, it looks to us like for most tree species on Earth, tree mass growth increases continuously with tree size. And there will be exceptions. If a tree crown gets struck by lightning and it loses half its crown, growth will decline. But for a healthy, happy tree, it'll keep growing more and more. Each year, it'll put on more mass than it did the year before, up to the largest trees on Earth. So the reception of the paper, I would say, is either positive or neutral. I was gratified to hear from other people that some groups saw the paper, read the paper, and went, oh, this can't be right. And then went and looked at their own data, and by the end, they went, oh, yeah, this is right. So that was very gratifying. The neutral responses are the ones I consider just the paper is getting cited, and it's getting cited at face value. No one's saying, it's not getting cited because everyone's trying to say this is impossible. But the extremes of the distribution here and here are what's really interesting, because there was a group of people who said, this is trivial, everyone already knew this, and they never responded to me, but I'd say, okay, point me to the paper, and they could not. And so, well, actually what you mean is you suspected this was true, and now you're probably kicking yourself because you didn't realize you could get a really high-profile paper out of it. And I've done that a bunch of times. You know how it is. You read something and you go, oh, my God, I just assumed this was true, and they got a real high-profile paper out of it. It happens. The other extreme was this is clearly impossible and therefore has to be an artifact. And so that group did submit comments to Nature, which Nature rejected after reading our responses to them. And then 3 of those groups joined forces and changed their tune some, and now they're mostly saying there are too many uncertainties to draw firm conclusions is what they're saying now. And in press, so you all have a chance, if it interests you enough, you can go, this paper is online in Functional Ecology now, and read through it and see what you think of their arguments. But since I'm the one giving the talk, I get to bring up a couple of them and refute them. And if they were here, they'd be arguing with me. And I tried really hard to not get in the weeds because I want to refute every sentence, and I'm not going to. But among other things, they caution that there's lots of error in repeated diameter measurements. That's absolutely true. And we talk about that error, and the critical thing is to be sure it's not biased. But a continuation of that point was that any bias towards eliminating more negative values than positive values could lead to the appearance of continuously increasing growth. So they created a data set to illustrate the point, which is fine as long as you say this is a made-up data set to illustrate the point, where there's this huge amount of error, and then they shaved off these gray points here. It's really representing constant mass growth rate or basal area increment. If you shave off these points, you start getting these curves that are curving up when you remove those data. And I was in communication with these people while they were producing this manuscript, and I said, that's great to use a contrived example to illustrate the point, but we can test this. There are data out there to test it. And here's an example where we had several species in the southern Sierra Nevada where we had tree ring series from them, plus diameter measurements. And so here's the model fit of continuously increasing mass growth rate from diameter measurements. And here it is if all you have is tree rings. Tree rings are not subject to the biases that were concerning them. You cannot get a negative growth rate from a tree ring. At best, you can get 0 if it's a missing ring. So I was disappointed that they raised the point and didn't go the extra step and say, but the available evidence so far suggests that source of bias is not important. They used their own longitudinal data from tree rings to do an analysis from tropical tree species, because in very seasonal parts of the tropics you do get annual tree rings. My disappointment here was they didn't refer back to the rest of the tree ring literature, which in the majority of cases indicates continuously increasing growth rate, but they wanted to analyze their own data. And they found no consistent growth trends with size. And this, I also brought this to their attention, but they never responded to it, is environmental changes. They had already published papers showing that for a given size of tree, growth rates had been going down through time, and they attributed that to a warming climate in these seasonal tropical forests. And so when they couldn't find a consistent trend, what's to say that if the climate had been steady, it wouldn't have been continuously increasing growth, but it's this declining growth trend that they had already demonstrated is why they weren't finding continuously increasing growth. I don't know if I said that well, but I'm still full of consternation over this one. They hardly mentioned the gold standard, that bookend of the largest trees on Earth that Sillett et al. Have dealt with, except to express some doubts about it because they misread the methods, as far as I can tell. They were saying, but remeasuring diameter at these incredibly broad diameter trees, they're some of the biggest trees on Earth, there's so much error in that, we don't know if we can trust this. But that isn't how Sillett et al. Did it. They had to measure the diameter to get a base diameter, but then they took cores and decided on the growth rate from the tree rings themselves, not from the repeated diameter measurements. So I think they missed the point there. And this is what I think. I think, this is, Sillett's work gives the bookend on what's possible in the plant world for growth rate. And they found continuously increasing growth up to the biggest trees. So it almost flips the question on its head. It's like the burden of evidence now seems to be, well, if the biggest trees on Earth can keep putting on more mass each year, why wouldn't the smaller trees on the face of Earth do the same thing? I was disappointed they didn't address the mechanism that we proposed is, here's leaf mass in giant sequoias against leaf trunk diameter. Here again is the second most massive tree on Earth. By the time you're up here, you have 0.6 of a hectare of leaf area. Leaf area doesn't go up and then plateau. It doesn't asymptote. It keeps going up through time also. So it's almost like a tree is like a coral reef. The more surface area it has, the more mass it adds, and the more leaf area it can add, and it just keeps getting bigger through time. So this increase of leaf area through time is rapid enough that it's outstripping the decrease in productivity per leaf that happens over time. So now we're getting into the spontaneous generation of facts. I was really interested, and this is something I could not put in the paper because it was a Nature paper and they have to be really, really short, but I really wanted to put the literature review in, and maybe I'll get it out there someday. But where did the belief in declining growth come from? And I think people are prejudiced by being mammals, because as mammals, we don't continuously increase. We have a growth spurt, and then our growth rate declines. But I couldn't find anyone who made that direct comparison in the literature, but I wonder if it predisposes people to expect that from trees also. But here are the 4 really big ones you find in the literature, and I'll go through those one at a time. Oh yeah, there's the prejudice one. But scale confusion I found to be the biggest one of all is it has to do with what's net primary productivity of individual leaves versus the entire tree versus the entire forest stand. So at the scale of individual leaves, it's really well established that productivity declines with tree size or tree age. A lot of that just may be due with hydraulics, because the bigger and taller the tree is, the more path length you have to move water, the more gravity you have to fight to get water up there. So productivity per unit leaf area goes down as trees get bigger. But look, here's a typical example is maybe it goes down 3 or 4-fold. It goes down, but it doesn't go down in huge, huge amounts. At the scale of the forest stand, it's also well established that after an initial increase, productivity declines with stand age. So here it is, stand's getting older and older and older. It peaks in its productivity, and then it declines. So here's what has happened is you've got declining productivity at the scale of the leaf, declining productivity at the scale of the forest stand. People have just assumed that it's also happening at the scale of the individual tree. And here's an example from the literature. This paper was on individual tree growth, and they cite these papers as evidence that individual tree growth declines. But this paper is about stand growth, and these two are about leaf growth. And so it's sort of this conflating of all these scales and assuming they all behave the same way. So you might ask, how is it possible that productivity can be increasing at the tree scale, yet declining at these other scales? And you can take that one at a time. How can individual tree growth increase as productivity per unit leaf area decreases? And it's simple. I've gone through all the allometric equations that are available, and on average, leaf area increases as the square of tree diameter. So a 100-centimeter diameter tree has 100 times, am I getting this right? It's the time of day when I can't do math. If you, let's put it this way, if you double the diameter of a tree, its leaf area will go up 4-fold. Did I get that right? Thank you. I'm struggling today. And when you saw I did show the leaf area through time or through size for giant sequoias, it didn't look like it was going up as a square. I think by the time the tree gets really, really, really big and it's reached its maximum height, it looks like it goes up linearly. But still, it's going up a lot as the trees get bigger. At the scale of the stand, you just get fewer and fewer trees through time as the trees get bigger. You're losing trees to mortality. And yeah, here it is. So, and there's even a nice paper that demonstrated all of this, that mass growth rate of individual trees was increasing through time in their even age stand, but there was so much mortality as the trees got crowded and forced each other out that at the scale of the stand itself, productivity was actually going down. I do think part of the scale confusion has come from terminology. Like here is a paper, here's stand age, and here's above ground net primary productivity. It says tree here. It's not tree, it's stand. And from context, that's clear, but if you're just flipping through that paper and you see that, you see tree and you go, oh yeah, trees, productivity peaks here and then it declines. But no, that's the stand level. A real interesting one is what I call unintended conversion of a hypothesis into fact. I think this is a lot more common than we would like to admit. Here is a paper by Kira and Shidai. I'm not quite sure how to pronounce this, 1967. And you've probably seen some version of this at some point. Stand age on this axis, gross production along this axis, stand respiration here. So the difference between the two is net production. So there's net production peaking and then declining for this stand. They very clearly said, this is hypothetical. They said it in the figure caption, they said it in the text. And they also said, and we think this applies to stands and to trees. Then Gene Odom saw that, and he's one of the most famous ecologists of the 20th century, and he grabbed it and he published it in Science up here. And he did, in the text, call it hypothetical, but in the figure, it doesn't say hypothetical. And if you're flipping through quickly, this is why probably that this ended up in a lot of textbooks. This figure ended up in textbooks, and yet it's a hypothesis that was untested, and it got converted to, quote, fact. There's also false dichotomy, and I've seen this in a couple of sources. I quote one source here where biological growth is intrinsically exponential. One cell divides to become two, two divide to become four, four to eight, and so on. But you can't keep up exponential growth for very long because pretty soon the whole universe is biomass. The false dichotomy comes from, well, if you can't have exponential growth indefinitely, that means growth has to decline. But that's just not the case. Growth can increase continuously at something much less than exponential. And there are some sources that people have cited that as far as I can tell, I've read them and I can't find that they say growth rate declines with size. One of these is Osman's Principles of Forest Yield Study, 1970. It gets cited a fair bit as saying that. I could have missed something. There's a ton of figures and text in the book. I found this one figure that could be misinterpreted as saying that. It's some really amazing work on mass growth rate, or it's actually volume growth rate, but it's almost equivalent to mass growth rate, by dissecting trees and peeling tree rings off and all that sort of thing. But it's an even-aged forest stand, and this is probably the point, if you read the text, where canopy closure happened and competition kicked in, and this was a slower growing tree at the start, and it's getting suppressed here. And right next to it, and the interpretation in the text is this one was going up, then canopy closure, it started to decline its growth rate, but then they thinned, and it took off again. They thinned the stand. And so I think people maybe have looked at the left-hand one of those and said, oh, there's proof that growth rate increases and then decreases, because they weren't interpreting it in the context that's given in the text. So why all of this matters? It matters for life history theory, theories of plant senescence, and modeling feedbacks from the forest to global change. A couple of well-established things are that reproduction is costly to trees. There's really no doubt about that. That often comes from masting studies where in a given year a tree suddenly puts out a huge amount of reproductive effort and its wood growth goes way down for that year. It's put its energy into reproduction but not into wood growth. It also appears that both absolute and relative allocations to reproduction increase with tree size. So as you get bigger and bigger and bigger, not only are you putting on more absolute effort into reproduction, but more relative effort into reproduction. And there's a really good review for that in one of those books I showed earlier. I thought it was a well-done coverage of all of that. Some authors have pondered whether increasing allocation to reproduction drives a decline in growth rate through time. What we think is going on is, here's that tree mass growth rate here, tree mass and mass growth rate. Reproductive allocation, it's increasing in absolute and relative terms in this diagram here. And I've had some people ask me, but what about, they'll point out the study about a masting event that shows growth rate declines when trees reproduce. Well, I think the proper interpretation is something like this. You still have mast years where a bunch more energy goes into reproduction, and the mass growth of the whole tree goes down, but on the whole, it just keeps rising through time, even though you've got these variations from year to year. Theories of plant senescence. A declining growth rate this is a fairly recent review on the topic it's a Tansley review in New Phytologist. Declining growth is considered a hallmark or defining feature of plant senescence. And this is the figure out of that picture. There's more and more evidence that certainly the woody species just may not senesce, and I make this distinction here. Senescence is endogenous, so it's an internal clock or something like that that causes a decline in physiological function with age, ultimately leading to death. So I'm senescing. My beard is turning gray. I'm getting wrinkles. I'm a senescent organism, but maybe woody plants do not senesce. They definitely do age. I call it aging, and that's exogenous things that cause them to decline. So you're suffering the slings and arrows of time. A lightning bolt takes a limb off, or a pathogen invades you. I heard that someone once decided to calculate what would be the average human lifespan if we didn't senesce. It's a real interesting question. And they came up with something like 700 years. Some people would live thousands of years. Some would only live 1 year, but on average, 700 years. Because eventually, we'd be hit by a car, lightning would strike us, we'd fall off a cliff, we'd catch a horrible disease. We'd end up dying, but it was from exogenous forces, not from senescence, which is endogenous. And here's some useful reviews to look at that are casting doubt on whether woody plants actually senesce. So modeling feedbacks to the global carbon cycle. Sometimes our results have been misinterpreted as meaning that old forests are really rapid net accumulators of carbon. They're not. They can still be net accumulators, but it's usually at a really, really low rate. Here's the analogy I use. Here's a forest stand. A young forest stand is the bucket. The amount of carbon it's pulling out of the atmosphere is really a lot. The rate is really, really high. The loss of carbon to mortality is really low. So what you end up with is you don't have much stored carbon. Here's the water level down here, but it's rising really rapidly. Old forest stand, you have a moderate carbon uptake from the atmosphere, and you have a moderate loss to mortality. And the net effect is you have a lot of stored carbon, but it's nearly static. It's not changing much through time. So the way I've tried to phrase it, because then some people ask me, well, then what did you find? It's just that big trees are disproportionately important parts of the carbon cycle. And an example is for our western old-growth forests that we put into that study, only 6% of trees were greater than 1 meter in diameter, and yet they accounted for a third of the carbon sucked into the forest every single year. So they're disproportionately important in the dynamics of carbon in the forests. We also know that the numbers of large trees are particularly sensitive to environmental changes. And I'll go through some examples here. Across the West, tree mortality rates have doubled over the last few decades, just in general for all sizes. Jim Lutz's work from Yosemite shows a decline only over about 60 years in the proportion number of large trees on the landscape there. And more recent work showing that globally large trees often die disproportionately during droughts. And here's just another recent review about declines and loss of large trees all over the world. So if we are going to understand and predict feedbacks to the global carbon cycle, part of the inspiration to do this whole study was that models of the global forest carbon cycle were more and more moving into demography and trying to use shortcuts to incorporate individuals. And it seemed important to get it out there, to get those models right. Because right now, if you make the wrong assumption about growth rate with size in trees, you could tune the model to get the right answer, but you might be getting it for the wrong reason. So then when you project into the future, the model could fall apart and give you an answer that doesn't make any sense as to compared to what really will be happening. So my grand conclusion is that tree growth rate does increase continuously with tree size, and that does matter. So thank you for your attention.
Questions for Nate? You mentioned this a couple slides back that the more large trees are dying, or the high proportion of large trees are dying during these droughts. Is that
You want to delve into this in a little more detail?
I think they'd be more resilient being larger trees and smaller trees. So
yeah.
I want to know what they can find.
What's really interesting about this figure, and I might not get this exactly right, but some are open squares and some are closed squares. The closed squares are driving the trend, and the closed squares are mostly pines killed by bark beetles. So it's mostly Dendroctonus that is the genus Dendroctonus may be driving a lot of this, and they say that in the paper. They also, they have a whole bunch of different analyses, and proportionally, good enough. I can't get into the weeds on this yet. But what we're finding in the big drought that's just happened in California is indeed pines. The biggest pines are dying at enormous rates, and the smaller pines are doing better. But if you look at other species, like with firs, there's almost no difference across size classes. All size classes are dying at the same rate during the drought. And if you look at incense cedars, it's the smallest trees dying at the highest rates, and the big trees are not even dying at all. And if you look at the mechanism, it really looks like it's their co-evolved bark beetles that are driving that. Each of those genera has its own co-evolved bark beetle, and they prefer trees of different sizes, and that seems to be a really important factor here. So if you could eliminate bark beetles out of the picture, it would be really interesting to figure out what does this curve look like. So bark beetles rule the world. Yeah.
Given how hard it can be to measure carbon accumulation in old forests, do you think that the conclusion that carbon accumulation decreases as the forest gets to a certain age, do you think that conclusion might be susceptible to some of the same problems that the case of tree growth decreasing with size?
So this
or do you think that's more well established?
This is about carbon accumulation rates of old forests, right? Because there's no doubt that old forests hold lots and lots and lots of carbon, but the net rate of change of that giant pool on the landscape, I think it is really well established, isn't very fast. Some groups say, if you don't have a disturbance, it can just keep creeping up through time. You have more and more net carbon storage on the landscape. But if anyone else has other information, tell me. But I think all the reviews out there show that the net rate of accumulation is fastest in the youngest stands.
And that's rate and also net amount of. So rate decreases and.
But the net storage goes up. Yeah. So old forests definitely hold more carbon. It's just the rate of change in that amount of storage slows way down. Unless there's a disturbance, yeah.
I have a question about suppression in terms of when you're thinking about larger trees putting on more mass than smaller trees, but then you also sort of have this caveat where suppressed trees, even if they are large, don't put on as much carbon. And I was kind of curious, do you think that the study was just capturing the fact that smaller trees tend to be more suppressed in a lot of forests?
Yeah, great question, and I probably didn't explain that well enough. We did a sub-analysis of what is mass growth rate of trees in the absence of competition. And even then, the smallest trees had the lowest rate of carbon accumulation. And you think about it, and picture a little sapling that's this tall and this big around. Even if it puts on a hugely fat ring because it has no suppression whatsoever, it is just not putting on much mass. And you get up to a giant tree, and it can put on this really narrow ring and put on a lot more mass than that little tree did. So a lot more work could be done there, and it needs to be done there to figure out what would be the growth trajectory of an ideal tree in the absence of competition. But for those something like 34 species that we looked at, generally the trend was continuously increasing growth. Yeah, and there's a question back there.
If a tree is putting on, let's just say, 2 mils a year, it's getting bigger each time, that's a nonlinear increase in cambium growth, right?
Say it again, please.
You can have a nonlinear increase in the number of actively growing cells in cambium.
Absolutely. Yeah, there's more and more cells all the time.
So you have a nonlinear increase in respiration through the tree's life.
Yep.
So how can a linear increase in leaf area compensate for a nonlinear increase in respiring tissue?
The axis where we showed it looked more linear increase, I think I'd have to look back again. I don't remember whether that was a mass axis or a diameter axis. So you're saying, the number of cells is increasing as the square of diameter, but if the leaf area is only increasing as linearly, why wouldn't you have a growth decline? My math isn't working in my head right now. I have sat down and worked it out, and it doesn't look like it's an issue. Because respiration, how much of net production is actually being respired? I again go back to the analogy of a coral reef out there, and it just has more and more surface area for gathering.
But the difference is the cambium is not gathering. It's only using.
Yeah.
I think the answer is that the heartwood is increasing also at that same rate as the sapwood cells are increasing. It's just lagging. And so you've got the amount of sapwood increasing linearly over time.
Oh, thank you. Yeah.
It's in parallel with the increase in the care.
So you're saying the cambium increase is linear and not linear?
The amount of xylem tissue or cambial tissue it would be xylem tissue, not cambial tissue.
Yeah, xylem tissue is the respiring tissue, not just cambium. And sapwood tends to narrow as the tree gets bigger and bigger and bigger. So, and you're saying that you think its volume growth is linear. Sapwood is getting narrower as the tree gets bigger and bigger, but maybe it's still increasing at a linear rate or something like that.
Right.
Yeah.
That helps account for the respiration.
Yeah.
I had one more hypothetical question. Lots of tree ring studies have shown that the oldest trees of any given species tend to be the slower growing individuals.
Yeah.
And so that suggests that perhaps fast growth rates lead to faster mortality rates. And you can kind of picture that if you have the biggest tree in the forest, it might be more susceptible to wind throw because it's got a bigger sail that can catch more wind. And potentially it has different allocations to defense or structural mechanisms. And some people have started to suggest that because of that evidence, indirectly, that if we have trees that are growing faster because there's more CO2 in the atmosphere, that trees may actually die more quickly.
Right.
I was wondering if you have any thoughts on that.
I'm wondering if, Steve, if this was a setup question, because I wrote a paper related to this topic that he was a reviewer on, and he was an outstanding reviewer. Held my feet to the fire on a couple of things. But I think the difference is if you're within a stand, it's the difference between within sites and between sites. Within sites, it's the slower growing trees die earlier. Between sites, so you go to a whole different environment, and within that environment over there, still the slowest growing trees die. But as a whole, that might be a less productive environment, and the trees on average live longer there. And the paper I put out argued that maybe at least part of that, if that's a climatic productivity gradient, is that the sites that have really fast tree growth tend to be warmer, wetter, something like that. That they're also the best for the insects and pathogens that attack trees. So like if you go down to the tropics, where you have a year-round growing season in some of these forests, and it's always warm and wet, there have been studies where somebody's purposely wounded the cambium of trees, and it's just like bugs and fungus go whoomp onto it and kill trees pretty rapidly down there. So I think the distinction has to, so back to does the increase in atmospheric CO2, is that going to increase tree mortality rates? I haven't given it deep thought, but my initial reaction would be maybe not, unless it's a structural thing because maybe the cell walls are thinner because the trees are growing more rapidly or something like that. But I don't know what the mechanism would be. There's a correlation, but unless you look at what the causation is, you may not be able to draw a conclusion.
Okay, let's thank Dr. Stephenson.
Thank you.